Hey there, folks. Today we're going to talk about a couple things here. Sedimentary structures and a little bit of a science called stratigraphy. Might know that strata means layers, and so this is dealing with sediments and sedimentary rocks, and sedimentary structures, of course, then are things that we find within the layers of sediment. So first things first, sediment is deposited in layers. Okay. Think of dust on your shelves. And if you don't dust for a very long time, you get dust building up layer after layer after layer. Well, that same idea works not just in your house, but at the surface of the earth, at the bottom of a lake, bottom of an ocean, stream, anywhere. All right. So sediment, dust, pebbles, sand, cobbles, whatever you want to size you want to use, piles up layer after layer after layer if it's allowed to. Well, we call those layers beds and sometimes bedding planes. Okay, so beds or bedding. When you did sedimentary rocks, you quite possibly, or when you will do sedimentary rocks, we've already done them this semester here. When you do sedimentary rocks, you'll see that some of them are visibly layered. Some of them are not. Rest assured that they all are or were built up layer by layer, even if you can't see those layers anymore. And the other thing that's important here is that the layers are always horizontal. Sorry, I had to pause it there. These layers were originally horizontal, okay, flat. Like this. We're looking, of course, up here, where it's very easy to see. But as I said, even down here where it obscures out, this is a bunch of, this is a sediment slope right here. Whole bunch of sand or whatever you want to say, dirt built up in front, so blocking it. But even when you can't see the layering, it is still indeed there. All right, so we're going to talk about a handful of rules about these beds, okay, about layers. And they're all going to be principle of this, that, or the other thing. Okay, so the first one is principle of superposition. The principle of superposition tells us that in an unaltered section of rocks, we can expect to find the oldest rocks at the bottom and the youngest rocks on top. All right, think back to this picture right here. Okay, if I asked you where the youngest rock was and where the oldest rock was, you might just have guessed that. Okay, well, the youngest stuff is at the top, and the oldest stuff is down here, somewhere again behind this pile of dirt at the bottom there. Some of you might not have jumped to that answer, but understand it now. I like to use the analogy of mail building up on your table. Okay, every day the mail comes in, you bring it in, you pull out what you need, and you toss everything else on the table. At least that's what we do at the Joppo household. Okay, and all week long, next week, whatever. So let's say, just looking at that pile of mail, that you want something that you know came a couple weeks ago. Let's just keep it to 1 week. All right, so let's say mail comes Monday through Friday. It's Friday. You knew that you got some pizza coupons in the mail on Monday. All right, where are you going to look in that pile for those pizza coupons? The top of the pile, the middle of the pile, the bottom of the pile? Well, the bottom of the pile, of course. Why? Because it was there first. All right, it was Monday was the first day of mail. If they came on Friday, you would look at the top of the pile. Makes perfect sense. Well, the same thing is true with sediment. The sediment way down here, okay, ignoring again this slope here. The sediment way down here, okay, was deposited before the stuff up here. So this is older, and that's younger. The key here is in an unaltered, undisturbed. If your dog comes around or somebody comes along and shuffles that mail up looking through it, kind of just willy-nilly, who knows where those pizza coupons are now, right? That's altered. So in an undisturbed, and scientists have ways, geologists have ways of knowing whether or not something was disturbed. So first rule is if you're looking at sedimentary rocks like this, you can expect the oldest rocks to be on the bottom and the youngest rocks on top, and we call that superposition. Second one is principle of original horizontality. Horizontality. I can guarantee you spell check did not like that word way back when. It's used to it now. I mentioned this to you a couple minutes ago that these layers are flat, okay? Horizontal, like if you have your textbook next to you or a notebook, like the sheets of paper in there. That's how sediments build up. What's difficult to, and I don't think I ever added a picture to this, I always maybe just draw on the board, is imagine a bowl, a soup bowl, whatever, a cereal bowl, okay, that has a sloped side to it. What's difficult to imagine, though, is that the sediment doesn't mirror the shape of the bowl, if you follow me, okay? You don't get deposition on the sides and then down to the bottom and then back up the other side. Everything rolls down to the bottom because of gravity. So what you have is you slowly fill up the bowl from the bottom up, just like if you're pouring milk in your cereal bowl or soup in your soup bowl. Well, the same thing happens with sediment flowing into this lake or to an ocean, okay? It goes all the way down to the bottom, so you still get those flat layers. Otherwise, you'd get curved layers, kind of like an upside-down rainbow. You follow me? So we don't get upside-down rainbows. We get curved layers. So it's easy to picture this on the ground, on your television set or your shelves. We were talking about dust building up. But in lakes, it works the same way. All right, principle of lateral continuity. This one's a little more, and again, no pictures. I got to add pictures to this stuff. I thought I had. Principle of lateral continuity tells us, quite awkwardly, that a rock layer extends outwards in all directions until it ends. Okay, so a rock layer goes until it doesn't go. Well, what the heck does that mean? Well, in a situation, in reality, let's pretend that you're standing here, okay, and that you're actually looking across a valley, and that on the other side of the valley you basically see what's here, okay? In other words, you're here, and you look across and you see exactly this. What original horizontality tells you is that you have every reason to assume that these layers that you see across the valley, my mouse just disappeared, there it is, are the same layers that are underneath your feet. You have every reason to assume that the same environment made those layers. They were made at the same time, and they're made out of the same stuff. That's a rule that needs to be made. I often call these the well duh rules, okay? But because they make sense, they're common sense. But somebody had to state them. Somebody got, believe it or not, credit for these rules. Some of the founding fathers of geology, okay? So you noticed what I put here then. I'm starting to introduce this idea that rocks are products of their environments, okay? Rock layers equal environments. Sand could be a desert or a beach. Shale, which was mud, could be a lake or a marine environment. You have to look for other factors to see. So on and so forth, okay? So it makes a little more sense, perhaps, if you think of this in context of environments, okay? Let's pick an environment. Let's pick a forest, all right? You're in a forest, and you're in the trees in the forest, and you walk through it. At some point, the forest is going to end. What might you expect to come into? Well, just from your experience on Earth here, you might think you'd come into a field, right? And what will happen is that forest will gradually thin out, and it'll turn into a field. Fields are dominated by grasses as opposed to trees, all right? And then that field might go into, let's say, a marsh, all right? And then we'll see some different changes as the soil gets wetter and wetter and wetter. The point is that we're used to walking through this at the surface of the earth. The idea is that it sort of mirrors in the earth as well. Okay, we got 2 for 1 here. We got principles of cross-cutting relationships and principles of inclusion. I included these together because they kind of tell us the same thing, but about different situations. Principle of inclusions is actually easier. I didn't make it the bigger one, but we'll talk about it first anyhow. So picture a hunk of rock, okay? A conglomerate of a whole bunch of different things. You got sand grains, some pebbles, all kind of stuff in there. What principle of inclusions tells us is that any one of those pieces inside of that rock is older than the rock. Okay? Again, if you think about it, it makes sense. Who thinks about that? Well, that's another question. But you couldn't have made that rock if you didn't have those pieces parts. And quite likely, to take this out even further, there's probably a huge range of variation in how old those pieces parts are. That's why it's not really great for scientists to be able to age date sedimentary rocks. You get a huge factor, okay, a huge variable. I'm sorry. You'd be able to say this rock is no younger than or no older than based on however many samples you take, and you better take a lot if you're doing a sed rock. We tend to like to date igneous rocks. They're much neater and smoother testers. So anyhow, so back to principle of inclusions, not to go on bigger tangent here. The idea that is again, the inclusion is older than what's it's included in. All right. Cross-cutting relationships. The disrupted pattern is older than the disruption. Let's go back to here. So here's your pattern, all right? You've got your rock layers all the way through here. Let's say there's a big old volcanic intrusion here. Remember igneous intrusions? All right. There's a big old dike system coming through here and sills and whatnot. What's older, the rock here, the layers, or the igneous intrusion? Which is older? Well, the rock layers, of course. The igneous intrusion could not have intruded into it, right, if it was not there. Now, I just happened to mention to you that igneous is a great thing to date, so we could get a big solid date on this imaginary igneous intrusion that I'm making here with my mouse. And then we would know that the sedimentary rock is older than that. Okay, not horribly helpful, but relatively helpful. So principle of cross-cutting relationships and principle of inclusions. All right, so those are your principles. Pretty straightforward. To be honest with you, superposition's the big one. It's really important that super important that you remember that. Original horizontality is also important. If you're driving down the thruway, lots of beautiful rock cuts there. Some of them nice and flat, some of them all wavy like a roller coaster. What this tells us is something happened to those rocks to make it look like a roller coaster went through there. Okay? Originally they were flat just like all the other ones. And then it's some other geologist's job, some geophysicist probably, to come through and say, oh, well, there was some plate tectonics going on here that warped these layers, and so on and so forth. Lateral continuity, sort of a higher level concept. And these two are just to help you when you want to relatively date stuff. All right. So just a little more vocabulary here. A formation. Okay. Formations are made by geologists. Formations are made by nature. Formations are named by geologists once they're studied. All right. And it's just a group of rocks. That picture I keep rolling back to has a name because somebody has studied it. Now, formations come in one of two types. They could be of a single rock type or multiple rock types. Here, because we see different colors, we're going to just assume from this 100-yard view that we have here that the dark stuff is a different colored rock than the light stuff. Okay? If there was no dark stuff here and it was all light, let's call it a sandstone, all right? We would say it was the such and such sandstone, usually a location name and the rock type. Here we have the Utica Shale, for example. But we'll call that the Tempe sandstone. Okay, Tempe, Arizona sandstone. I have no idea why Tempe came into my head, but so that's one type of rock, where it was first found, studied, a great example of it, whatever you want to say. So we know where it's found and we know what type it is. If, however, it's multiple rock types, down here you see the word formation, they would just say the Albany Formation, or to go back to my example of Tempe there, because we did see multiple colors in there, presumably multiple layers. We would call that the Tempe Formation. And you'd have to go to a handy-dandy journal article or something like that and look it up and see what are the rock types in the Tempe Formation. Okay. So it's just a way that they refer to things. If you see the word formation, it means that there's multiple rock types. If you just see a rock mentioned, well, guess what? That's the type of rock that it is. All right, another vocabulary word, a contact. A contact is a boundary between two different formations, and it represents a change in the depositional environment. Now, I mentioned to you already that rocks are environments, right? And are products of environments. And deposition just means that the sediment had to be put there. So when we see a change in rock type, we're seeing a change in an environment. And it's also important to understand that not all environments make rocks. Some environments destroy rocks. Okay? So there might be a gap in time when you switch rock types, when you switch between formations. The contact between those layers might be what we call an unconformity. And you'd have to go there and look at it, test it to see. But you don't know until you look. So it might not be a depositional environment that exists for a little while. It might be a destructive environment, or it could be just a change to a different type of environment that still makes rocks. So just vocabulary. Okay, an unconformity is a gap in the rock record. Okay, here's a better definition of it. Okay, a gap in the rock record, which equals a gap in time. It could equal a weathering event or a period of no deposition. I'm not sure why this is way out here. Okay, so just taking another scenic view here. The Kaibab limestone. Well, what kind of rock do we think the Kaibab limestone formation is made out of? Right, it's made out of limestone. Good. Where do you think it's found? Kaibab. Okay. The Toraweep Formation, what's in that? Well, we don't know, but it's more than one type of rock because they're not listing a particular type of rock. Where is it found best? Somewhere called Toraweep. Coconino Sandstone. All right, you get how this works. And then in between these here, you see these black lines drawn in. Those are the contacts. And it's sometimes going to be very obvious, especially when the color changes, okay? Whether or not there's a change in the rocks. It's not something most folk would recognize just walking by.